Hello navigators, welcome back. In today's lecture, we are going to talk about understanding this new solver, cavitating foam. We have already discussed one solver in which we solved cavitation. We'll also see that what is different in this particular solver compared to other one that we have already discussed. Let's get started. This particular solver, cavitating foam, is a transient cavitation solver in OpenFOAM, and it is based on homogeneous equilibrium model. In this particular model, we consider that the velocity, temperature, and the thermodynamic equilibrium between the vapor phase and the liquid phase is there, and it accounts for the compressibility. We assume different compressibility for liquid and vapor. Unlike the one that we have discussed, the phase change foam, in that we have not considered the compressibility, that was incompressible. And this particular solver, cavitating foam, considers the compressibility of the different phases as well. We all know that vapors are more compressible, or it can be compressed compared to liquid. It is suitable for cavitation inception and pressure wave propagation. Since it is compressible, therefore we can see pressure wave propagation. However, in incompressible, since the nature of incompressible flow, or the incompressible Navier-Stokes equation, is elliptical, therefore you do not see any pressure wave. These are the equations. Compared to phase change foam, we see that there should be only a divergence of velocity, which is taken care of while solving the pressure Poisson equation. But here we solve the continuity equation, then the compressible momentum equation, and then a closure equation is used, which is called the barotropic energy closure, and we do not solve an energy equation explicitly. The liquid vapor mixture is assumed to be in thermodynamic equilibrium, and the density pressure relation is given by a barotropic model. We will also see that what are the different barotropic model are present in OpenFOAM. This barotropic compressibility model, it interpolates between the liquid equation state and the vapor equation state. We will also see that if we have liquid here and some other property here, it makes sure that the transition here is smooth. There are different models for that. You can have 3 different models. It enables the simulation of rapid density changes and pressure wave during cavitation. There is a tutorial already there in OpenFOAM for a throttle device, in which you have a large diameter tube and then a very small diameter tube, and from here the liquid must pass. Here we see some cavitation close to the junction between the lower diameter pipe and the high diameter pipe. Here is the overall algorithm. It uses a pimple algorithm, and a large time step is possible, and it converts the pressure velocity coupling. We'll also see the key steps which are there in the solver, and it also supports turbulence modeling, and you can pass the turbulence properties using the standard turbulence transport model. And you can also have LES, which is often used in high speed cavitating flows. So these are the typical applications which are here, but the most important part is this, that it captures the compressibility driven shock waves. Whenever there is some bubble which forms and then suddenly changes into liquid when the saturation pressure is adverse, then in that case instantly all the fluid surrounding that bubble goes to that location, and that creates a shock waves. So you will be able to capture that kind of a shock wave using this particular solver, cavitating foam. And then let's talk about the contrast between the interface change foam and this. So the flow type that this solver consider is compressible for cavitating foam and incompressible for here. And here the interface is implicit because two phases will have widely varying densities. For example, the water vapor have density around the density of air, but water has the density of 1000. But here we have to explicitly use a volume of fluid method to capture different phases. Then the phase change is via barotropic model, but here we have to define an explicit mass transfer model. In both the cases, an energy equation is not solved, and here the primary variable are this one, which is different. Here is this volume fraction, here we have density, which is used to track the interface. And the main use cases are in which the shock like cavitation dynamics you want to capture, and here you want to capture the interfaces while cavitation is happening. For example, there is a object and here a bubble is forming due to cavitation. This particular interface you want to capture. In that case, you will want to use this particular solver instead of a cavitating foam. In cavitating foam, the interface capturing is not that great, but you will have all the shock waves that are generated due to cavitation. Now let's look at the solver. Go to your OpenFOAM folder, and if you go to application, solvers, multiphase, here you will see cavitating foam. Inside this you will see CavitatingFoam.c, and you can see the main loop. Here the simulation starts, and after starting in the pimple loop, it solves for the continuity equation, which is the rho equation. You can see here this is the continuity equation, and then it solves this. This is the pseudo volume of fluid variable, which is derived from the density. You can see this particular equation here from the density and the saturated density for liquid, and similarly for vapors. Using this, you find this, the volume fraction of vapor, and similarly the volume fraction of liquid. These are all derived from density. Then after this, you solve the momentum equation, and then using the pimple corrector loop, you solve for pressure. And here remember that in this pressure equation, you will see that first an equation of state is used, which is something like this. Here you can see P is directly assigned, and then if there is non-orthogonality, then an equation is solved. If there is no non-orthogonal correction, then you will directly get this, and this particular solver will be much faster compared to InterPhaseChangeFoam. Let me also show you that what are the different barotropic compressibility models that I use. If you go here, you will find that inside the thermophysical model, you have barotropic compressibility models. Inside this, you have these different models. You have Chung, you have linear, and you have Wallis. Let's see linear one. When you define this barotropic model as linear, all these models, they give you the compressibility. The compressibility is equal to this times, and this gamma is decided here. Here the gamma is this alpha b. From this you create a linear variation between the compressibility of the vapors and the compressibility of the liquid. It's straightforward. Let's also look at Chung. In Chung you have this, so it is some kind of a square root as well, and from this you again derive this psi. Similarly, from Wallis et al, you have this kind of a formulation. You can figure out that what they are doing. You can plot the variation of these two and figure out that how it looks. We are not going to do that in this particular lecture. We are just going to look at this particular example, and this particular model is also used in the tutorials. We'll copy all the variables that are used in the tutorial, and also let me run this tutorial test case as well first. In order to do so, let me directly open that. Here you can see I have ran only 2 iterations of this. You can see there is liquid that is coming in from here. Here this vapor one, that means this part is vapor and this part is liquid. Water is coming from left, and then it is going through this smaller pipe, and this is the throttling device, and then due to very rapid change in the pressure in this region, you see this vapor formation, and the next you can see this is just propagating towards right. And let's also look at the velocity. You can see here, you see that the velocity is also getting affected due to this cavitation effect. Now what we are going to do is We are going to take the example that we have taken in the case of InterPhaseChangeFoam. Let me take that and change this to cavitating foam. Now here, let me just go to cavitating foam, clean this. We don't need this particular folder. We are going to work here. This is the cavitating foam that we have just copied, and here let me show you the overall domain. We want the flow to come from the left and then hit this particular object, and due to any pressure change, if it is close to the saturation temperature or below that, then it is going to convert into vapors. That is what we want to simulate, and let's see if the values that are there in the tutorial will work, because this is a test case that we have randomly selected, and we'll see that whether we can simulate using those values or not. But here, apart from the actual values, we are going to learn that how we can set up simulations for cavitating foam. So first thing is we have to set the constants. So always start with constants, because here we set all the physical properties. So these thermophysical properties we are going to take from the tutorial. We have to define these few things only. The barotropic compressible model, we are going to take linear, and these are the variables that are required. This is a compressibility for vapor, compressibility for liquid, and then the saturation density for liquid, and then the saturation pressure for the phase change. And this is the minimum rho. In the transport properties, we have to set the properties for water and vapor. We don't need this. Let me also check what are the properties which I use here. This is water. These coefficients also not required. And these are the values that were there in the previous simulation, but here we are going to use this. There won't be any surface tension. Sigma will also be 0. Now here, since the first phase is vapor, therefore we have to define vapors here. Vapor is 0 everywhere, and everything else we want it to be calculated. Now the next thing is we want to set this pressure. Here the pressure variable is the standard pressure, and here the unit is going to be the same, and the value that we are going to use is this only, and the outlet we want to drive this a fixed value which is equal to this, and this should be 0 gradient. Now let's look at velocity. Velocity we are going to keep the same, 20 meter per second. Now let's look at the turbulence property. We are going to use laminar for now, and now look at this. Let's change this to cavitating foam, and here we need one more variable, which is max acoustic CO. This is the acoustic Courant number, and this we are setting as 50, and this we have to set a little bit lower. Let's start with 0.5, then if we will see that whether we can increase this or not. And in the FE scheme, we are going to use the same scheme that is used in the tutorial. Here is scheme to solve for the continuity equation. This is for the momentum equation, and n omega for added turbulence properties. We have not added it. If that is added, then this will be used. And these are for Laplacian, and this is also for turbulence. And here, now since there is no interface, there is no volume fraction, therefore we are not going to solve like this. This also I have taken from the tutorial. This I have changed from 1 to 0.7. I also added these some non-orthogonal characters, because in the tutorial the mesh is orthogonal, but here we do not have an orthogonal mesh. These all are the same. Here you should note that some added variables for which we are going to solve are rho and rho final. We are not going to solve for alpha v because that is just derived from rho. Now let's try to solve using these values. We are going to first clean everything and then when cavitating. These are thermodynamic properties. And rho is missing. We forgot to initialize rho. Remember that these vapors, these are just required for the initial values because these are derived from rho, and rho we need to define. So I'm going to use this. Here at the inlet we have a fixed value, at the outlet also we will have a fixed value. This is the fixed value everywhere that we are going to have. Let's run this. So it's running now. Let's also change this, the control dip change is to 0.01 so that we have more number of values. We'll wait for this to complete a few number of results. This is running very slow. Let's see what is going on. Here at the inlet we have some weird pressure, so this should not happen. We should keep this inlet far away from this particular object. Similarly for the outlet and these balls, the domain is much smaller. You should see our lecture on compressible flows to find out the effect when for compressible flow the object is very close to the walls. Let's look here. So we can see that from this is vapor is 0, that means there is no vapor here. This is all water, and here some vapors are forming. So you can see something is going on. This may not be correct, but we also don't have anything else, any actual values for this particular scenario. I have taken these values, the thermodynamic properties, from the case when the simulation was a throttling device. Given this, with this also you can see some cavitation happening here. This cavitation happens when this reaches below the saturation pressure, and this starts to change the phase. This has started to change the phase. Let's look at velocity. Velocity is also a very high value here. Apart from that, we don't see anything else. You can change this to a little bit lower value. Our inlet velocity is 20, so let's try 40, 2 times of that. With that, we see a nice gradient, except at this point. So this also could be due to our mesh resolution, which is very bad here. I chose this particular mesh because it takes a lot of time to solve all this, but the purpose of this particular lecture is to show you that how do you set up. Please let me know that what you solved using this particular lecture, what you learned from this, and were you able to solve whatever you were solving when you took help from this particular lecture. With this, we are going to stop. See you in the next lecture. Thank you.
Thanks for watching, and if you like the content of our channel, then please like, comment, share and subscribe.